So this is chapter 6, thermochemistry. When, as I've just said, for any chemical reaction, reactants go to products plus energy change. It's this energy change that we're investigating at this point. To understand energy change in a chemical reaction, you need to understand what we mean by the flow of energy. So what I typically do is ask students to construct a T-table. So given a T-table, on the left side you are to put system. On the right side of the T-table, surroundings. And we're considering the change in energy relative to the system giving off energy or absorbing energy. The system that in our case is the reaction of interest. Whereas the surroundings represent everything else. Now, when we talk about a reaction of interest, we're talking about reactants going to products. That includes both sides, the balanced equation. It doesn't mean, just to clarify, doesn't mean the system over here is reactants and surroundings is the product. That's not what this is. The reactants going to products is the system. Either the reactant going to products gaining energy or losing energy. Or having a zero energy change. And we'll show you what that is as we go along. Now, so when we talk about the reaction losing energy, that means we have a reaction taking place on this side and we have an energy flow that's moving from the reaction into the surroundings. Right there. So what this means is the reaction is losing energy and is therefore an exothermic reaction. The general definition of an exothermic reaction is that the reaction system decreases in energy. Now, the term losing energy or decreasing in energy is exclusively relative to the system or the reaction. It's not relative to the surroundings, because if you look at this, the surroundings is endothermic relative to that energy movement. SRNDGS is endo relative to energy flow. So when we use the terms, keep in mind that the terminology is based upon what the reaction is doing, not the surroundings. However, let me finish the definitions and then we'll show you the issue here. Now, if we take a reaction and we find that that reaction is gaining energy or is increasing in energy content, Where is it getting its energy? It's getting from the surroundings. It's coming from the surroundings and moving into the reaction system. So the reaction is gaining energy and is referred to as an endothermic reaction. And just as I indicated in the relationship of the surroundings to the exothermic, here we find the surroundings is exothermic. Relative to energy flow. So this is the starting point in understanding how we present the energy changes as they relate to chemical reactions and what they are defined to be. How is the chemical equation used to describe the energy changes? How do we use the concept of energy flow to describe the energy changes in a chemical equation? And we call these thermochemical equations. A reaction can be an endothermic reaction or an exothermic reaction, depending on the gain or loss of energy. Of course, it's the way we present that data equation that indicates, well, this is endothermic or exothermic. And so we're going to start with the exothermic reaction. And this is more symbology and placement of terms right now. So just to orient you with how energy is used in these descriptions. There are two ways to symbolically write an exothermic reaction as well as an endothermic reaction. One separates the energy value from the equation, one includes it in the equation like this. Consider the reaction 3H2 gas plus N2 gas goes to 2NH3 gas. Okay? There's an energy change that takes place with this, and we find that as part of the table in the very back of the book, we can look this up, because these are basic elements in standard state. You recall what basic standard state of elements is, 0, but the compounds have values, and so the energy gained or lost in the formation of a compound is its heat of formation. Well, we're going to call this heat of reaction as well as heat of formation. So the way that is illustrated is a delta H. That's heat of reaction, and it's called enthalpy. Enthalpy or enthalpy, depending on what part of the country you're from, I guess, or how much you've had to drink. Anyway, the delta H value for this one is published as a minus 91.8 kilojoules. Okay, you can look that up in the back of the book, saying this was for 2 moles of the ammonia, and I think the value in the back of the book is 45.9 or something like that. At any rate, this has a negative sign, and this is the indicator for exo reaction. The minus is the indicator for reaction. Now, the indicator for the reaction, if you incorporate it into the equation or write it as part of the equation, you put the number on the product side like this. You don't put negative signs in the equation itself. And it goes like this: 3H2 gas plus N2 gas goes to 2NH3 gas plus 91.8 kilojoules. Since we put the energy number on the product side, the placement on that right on the product side is an indicator that this is an exothermic reaction. So it's pretty easy to use. Now, both of these symbologies and notation methods are used on exams and in literature quite extensively. So it's to your advantage to keep that in mind. So you will be able to recognize just from the symbology whether the reaction is endo or exo. And it does separate from the equation, but we list it as a delta H equals a positive number. We don't have to put the signage, but like this: water, to evaporate water, H2O in the liquid form will go to H2O as a gas form if you add heat of reaction and the amount of 44 kilojoules of energy. We'll talk about the units in a few minutes. So this has no symbology before the number, which tells you that it is a plus, understood, and is an endothermic reaction. Or if you incorporate it into the reaction, the 44 kilojoules goes on the reactant side, which is an indicator of endothermic reaction. You can write it like this: H2O liquid plus the 44 kilojoules goes to H2O as a gas. And on the energy value, on the reactant side, says endothermic reaction, because you're putting it into the reactant side to produce the outcome on the product side. And of course the exo is on the product side, indicating that it is lost from the reaction at any rate. Now, now, with that in mind, we need to scoot through the stoichiometry of thermochemical reactions. Now, the reactions can be presented either in joules, kilojoules, or calories, or kcals, or so forth. But you need on the side as a sidebar to remember 1 scientific calorie is equal to 4.184 joules. So if the problem would ask you to convert back and forth or make conversions, that's about the only conversion factor you'll have to run into. Now, the coefficients are proportional to the energy values generated in a chemical reaction. And of course, those coefficients, if necessary, will be a limiting reagent. So really, you want to say the limiting reagent defines energy changes in chemical process. So let's consider, we'll use the ammonia reaction. is given to you like that. Calculate the amount of energy released when 638 liters of hydrogen gas is reacted with an excess of N2 gas at STP conditions. Rules 1 still holds. Convert to moles, solve the problem in terms of moles. And if they want something else, say they wanted you to convert to calories or something, then make the conversion after you finish the mole-mole relationships. So I've given you STP, so what does that tell you? Well, I've got 638 liters of hydrogen gas. How do I convert that to moles? Anybody? Real easy, guys. What do you do with 22.4? Divide. All right. So, given 638 liters at STP, we divide by 22.4 liters per mole, and that'll give us the number of moles of hydrogen. And so that's 28.5 moles H2 gas. So from the equation, we have 3 moles. Will generate 91.8 kilojoules. 28.5 moles in an excess will generate X. And so you can set it up as a ratio and proportion, or X can be adjusted by the coefficients of the, well, you're generating 2 moles just 3 moles in excess will give you the 2 moles of that and 91.8 kilojoules. So whatever we have, we've got 3 moles gives this, 28 gives X. We can simply set it up as a 3 over 28.5 to equal 91.8 kilojoules. Moles will drop out and solve for X. So X is equal to 28.5 times 91.8, and everything comes out in kilojoules. And so it's really a simple proportionality issue in that you just relate it to the equation, and of course the limiting reagent is related to the energy value. So that looks like 872 kilojoules. So that's the basic type of problem, and it's nothing more than you've already been doing. You're just applying the results to the idea of energy numbers. Okay, so we're given this equation, sulfur plus oxygen is SO3, and here's your exothermic reaction. Now, what do we do first?
Make it bigger?
Okay, we got a 6.44 grams of sulfur. Sulfur's 32 grams per mole. So going to moles. .201. And the idea is how much of the energy is released from the reaction. Well, 2 will give you 2 moles. Sulfur gives us a exothermic 791.4 kilojoules, 0.201 moles. Sulfur gives us X. So you can set this up in the ratio like this, solve for X, and you're through. Come out in kilojoules, and that's divided by 2 kilojoules. So I got 79.6 kilojoules negative exothermic. So really they're all about the same kind of problems. So once you understand the mole concept and how to apply that by ratio and proportion, God, you conquer the world. You know, that's not too much to ask, is it? So, okay, here's an equation, and I put the energy number on the end, and let's say you are throwing 35 grams of each of the reagents.
Can you make it big again?
Make it bigger, yeah, okay. 35 grams of each reagent into the reaction chamber, okay? Before you can work this, you have to determine the limiting reagent. And so, you remember how to do that? Okay? You convert to moles and divide by the respective coefficients. Smaller number is your limiting reagent. Then you go back up and work at your mole level and solve your problem. So, here we want to convert to moles, and this 17 grams per mole. So I got 2.1 or 2.06 mole for that one. And that's 1.09 mole for that, okay? So then we applied the, now what this all boils down to, if you took the equation and converted your, say, ammonia to a 1, you divide through by 4, and that's basically what you're essentially doing. But anyway, you divide by the respective coefficients and the smaller number, so 4 into that relationship, let me be sure, we get a 0.515 versus a, well, 1.09. So the smaller number is your limiting reagent, but we need to work from the 2.06 mole of ammonia. Everybody comfortable with that idea now? Any questions about that? This is just, you might look at this in red as a technique for determining the limiting reagent. The other reagent is going to be in excess when the problem is completed. So we have a 4 to 2.06, 1170 to X. So that's 4 moles to 2.06 mole, and that's of course the ammonia, is 1170 kilojoules to X, and solving for X kilojoules, that's 2.06 times 1170 over 4, and everything's going to come out in kilojoules. And that's exothermic. I should put a negative in here. I get 60 when I've got 2 sig figs in the data given, so we'll go 600 kilojoules, 2 sig figs, and make that, put a bar over the first zero. And you have to designate if a zero is in that answer, and you need it as a sig fig, you have to put a bar over it. The other one's not for sig fig, but it's roughly 600 kilojoules to 2 sig figs based upon 35 grams. So that's 2 sig figs minimum. Hess's law is a statement of determining heat of reaction by adding reactions together. If you have 2 or 3 reactions to get a net reaction, it's the sum of reactions to give a net reaction. The sum of the energy values, the algebraic sum of the energy values, gives the net reaction energy value. That is, individual reactions gives the net energy change or heat of reaction. Now these will require you to pay attention to some detail and invest some time if you're going to be able to deal with these. Okay, all I did was copy the 2 reactions. Now, there it is. Okay, so what we need to do is find the heat of reaction for this reaction. The reason these are used like this and done like this is that if you put carbon and oxygen in a reaction chamber and heated it, you would not just get CO2. However, your research or whatever you're doing may require just the energy in the formation of CO2 from these 2 reagents. In reality, mixing these, you would get CO2 and carbon monoxide in a mix, and that would be misleading in terms of this particular reaction. So what is done is reactions, what we call standard reactions, which are published in large volume books, are selected such that when you add these together, you get the target reaction. And the energy value here is the algebraic sum of these values here. Now, to do this, such that you get the net reaction. Now, the way I suggest doing this is keep one eye on this reaction here, and then look at the given reactions. Now, what you have the privilege to do here is you can reverse reactions, you can multiply the reactions to higher coefficient values, or divide them to smaller coefficient values. But whatever you do to these reactions, you also have to do to the energy value, because that is a proportionality. So we look at this and say, okay, what do we do to the first reaction? Well, actually, nothing, because carbon's on the left of the arrow, oxygen's on the left of the arrow, and so is, we have carbon monoxide, which we need to get rid of. So I'll come down here, I'll put a line under here, and I'll write reaction 1 again. Carbon plus half O2 goes to, you can even leave these states of existence out if you want to. I'll put them in anyway, just to. Okay, carbon monoxide gas, and the delta H1 is still equal to minus 110.5 kilojoules. Now, look at number 2. Well, CO2 is already over here on the right side, O2, and CO is on the opposite side. See, what you want to do is get rid of CO, and so we would write this one in the same way. Now, the reason I'm doing them over again down here is because this is a pattern you need to get into as you start working these. That's one of the simpler ones, and it solves itself. But wait till we get to the next couple. So I will look at reaction 2 and just write it as given. Seems redundant, but it has a purpose. So once we get the reactions given adjusted so that they'll generate the target reaction, then we add them together. This and this will drop out. Then I bring down the target reaction. Reaction 1, 2, if you want to do it like that, and it is C, carbon, plus half and half is an O2, so that matches. And it goes to CO2 gas, and delta H net is equal to delta H1 plus delta H2. And so I sometimes come over here because of room. Is equal to delta H1 is a minus 110.5 kilojoules plus a minus 283.0 kilojoules, and of course that adds to a negative something or another. I get 393.5 kilojoules. So that is the energy number for that reaction. And that one, so we go back and look at the, I don't know what it was in that action, but I'm hoping it's 393.5. Okay, so the target reaction is PCl3 plus Cl2 going to PCl5, and the net energy change is the target reaction. Given 2 phosphorus plus 3 chlorides, 2 PCl3s gives you this energy value, 6 minus 640 exo. And the second one, phosphorus, 5 chlorines, and PCl5. So as we look at the first one, we see that PCl3 is on the left side, but in the first reaction is on the right side. So what has to happen is number 1 has to be reversed to 2 PCl3s, going to 2P plus 3 Cl2, and the delta H becomes endothermic. I'll put a plus in there for effect, like that. Then we need to add that to the second reaction to get the target reaction. So we see PCl5 is on the right side, so we'll leave that, and we want chlorine and phosphorus, so we'll just rewrite the second equation as given. Can we add it together now and get the target reaction? So you check and see, well, I know I can get rid of the phosphorus, so that's one of the things that got to come out anyway, so that worked. But I'll have 2 PCl3s. Oh, where's my Cl2? Did I leave a Cl2? Oh, yeah, here. This cancels. This leaves me 2 there and 2 right here. So, yeah, I can add it together, but it's not the target reaction. But once I get the target reaction, I can divide it by 2. See, I'll get an outcome here. Watch. So the third thing is we'll add these together. This is 1 and 2 added together. So phosphorus will come out, and we're left with 2 PCl3. So you got 3 chlorines on the right and 5 chlorines on the left. So 5 minus 3 is 2 chlorines. And that goes to what's left. Let's see, that goes to I should have done it there, Cl2, yeah. And that leaves me a 2 chlorines right there. And then we have 2 PCl5s, and delta H net is equal to delta H1 plus delta H2. So delta H net now, being delta H1, is a plus 640 kilojoules, algebraically, plus negative 886 kilojoules. Okay, so we get a minus 246 kilojoules out of that, but it still does, the equation is very close to that, obviously. So in order to get the target equation, divide by 2. And so we get PCl3 plus Cl2 goes to 2 PCl5, and delta H net, our target, is equal to a minus 246 over 2 kilojoules, 123 kilojoules, XO. So this is what we're talking about in big picture. And some of them require quite a bit of effort. Sometimes it's a trial and error kind of thing. You turn them around and maybe you shouldn't have, or multiply too much or not enough, or take fractions and what have you. The Hess law equation will look a little more intimidating than it really is. Once you see me work through an equation and calculate the heat of reaction, you'll see what I'm doing. Okay, the Hess law equation looks like this. Now, the objective using this equation is to calculate heat of reaction. Okay, and the circle up here refers to standard thermodynamic conditions. So when you do, you will use this expression. what the equation is saying is that the sum of all the heats of formation of the products minus the sum of all the heats of formation of the reactions gives you the heat of reaction. Now that's pretty straightforward as you see it, but where do you get these heats of formation? Well, I showed you at the beginning of the course. You go to the thermodynamic properties table and look them up in your textbook. Now, on test day, they will be below the equation, the problem, and provide you with the values needed. So we're going to work out one. I'll just make up a combustion problem. It's pretty straightforward. Okay, so methane, combustion. Goes to, let me spread this out, I'm sorry, forgive me, CH4 gas, I'm going to need a little more room than what, 2O2 gas, goes to CO2 gas, plus 2 H2Os, liquid, we'll make it a liquid in this particular case. Now what it's telling you you need standard heats of formation for each of these reagents times the mole values. So for example, this one is 1 mole times the heat of formation. This one's 2 moles times the heat of formation, and so forth. So we'll look up methane is a minus 74.87 kilojoules per mole. So what I suggest in this, to keep from crowding the paperwork, is just put 1 mole times a minus 74.87 in kilojoules. And that's a minus 74.87 kilojoules in the product. The second one, oxygen, well, if you look up, that's a basic standard state element, and it's 0 for all you delta HFs. So this one is 2 times 0 kilojoules, and of course that's 0 kilojoules. On the product side, you have 1 mole of CO2, and so looking up the CO2 gas, it's a minus 393.5. kilojoules per mole and so forth, minus 393.5 kilojoules. And then 2 times the water, and that is a minus 285.8. Now let's fix to go off them. 285 point, let me see if I can get it in there. And so we double that. I get 571. Everybody up with me so far? Keep it up. All right. Isolate each side as reactants and products so you can keep up with your bookkeeping, so to speak. Because what you want to do is apply the sum of your product side and then subtract the sum of your reactant side. That's what the equation is telling you. So as I set this up, I say delta H of reaction. I'll take the product side and isolate it into, say, little brackets and parentheses. And I'll add that one to a minus 571.6 kilojoules. And by doing this, you keep up with your signage in your bookkeeping, so to speak, in as you build the equation you need to solve, and you won't drop a sign, and it's a little easier to see. And then you have subtract the reactant side. Well, that is 1 mole of the methane, so it is a minus 74.87 kilojoules. And I'm just going to bracket that one because the oxygen will be 0. I won't even include that. So now it's a matter of just simplifying the expression and algebraically adding the numbers. So that would simplify to a minus 393.5. That would be a minus 571.6. Minus times the minus is a plus. See how that, check mark that. So that's why you set this up like this. And plus 74.87, and I bracket it, and that's in kilojoules. And I'll put it on the end down there. And so this gives you an exothermic 890 kilojoules. I'll just leave it at that. So this is how that is, the Hess law equation is applied. You don't have all the adding up of equations, but each topic has its place in the chemistry problems that you'll work. As you see here, the thermochemistry of solution phase reactions. Well, one of the first things, you need to develop a perspective, a mental picture of what's happening here. You've got something being put into solution phase or in a solvent system, and then there involves an energy flow. So let's start with energy flow. In solution reactions. Now that includes maybe dropping a hot bar of metal into cold water, and you don't have a physical change to something else. It's not energy flow is what we're dealing with here in solution phase. So consider you have a container, and everything we're going to be working with for the most part is water. And say you have 100 mils of water. And I call this water solvent. And you'll see why as we get deeper into this. And so you have a block of metal that has at temperature T, and this will be in degrees Celsius as a matter of fact when you work these problems out. So this goes down into that, and so now the block is in the water, and so this is say water solvent at temperature less than T of metal. So what's going to happen is the energy is going to flow out into the water. And so what do we observe as far as changes in temperature? So if we start at 25 degrees, say over here in the water, and we put a hot object into the water is going to increase in temperature, right? So this is an increasing temperature of surroundings, because the water is receiving the heat as part of the surroundings. The block is the system losing the heat, so it's exothermic to the block. increasing temperature of the solvent water. So what you would observe, time, temperature, is just, you start out at say 25 degrees and you'd see that happen. And so you would have a temperature initial and a temperature final, and you'd have a change in temperature going on that reflects the energy transferred into the solvent system. Okay, and you'll probably have in there a thermometer measuring that temperature change, and of course you'd see it go up in the actual measurement of what's going on. So one of the first things you need to develop here is who is gaining energy, losing energy, and so forth like that. So giving that, now there's another energy flow in a solution situation. Let me show you that one also. Say you have acid plus base goes to salt, and H2O, a driving force, plus energy. The acid-base reaction is an exothermic reaction. Well, if you have a container of solvent water, volume of the solvent, right here, and then you have the acid solution, you pour that in, and then the base solution, and you add that in, you get the A-B reaction. So I like to, you won't see it like you would see a block of metal or something. It is the reaction going on giving products. And in the formation of the products, energy is liberated. And so I like to think of it in terms of A-B reaction, which you can't really see anyway, and I circle it in my diagram like that. So it's doing the same thing as if you drop a piece of metal in there. The reaction, because when you measure this, say put a thermometer in there, if you observe an increasing temperature, what are you measuring? You're measuring the surroundings only. So that's one of the things you need to develop in your mind as we go through these next sections. Who's gaining energy, who's losing energy, and how much, and where does these numbers go in the process of making calculations. And as we get deeper into it, I think you'll appreciate trying to decide on, well, where's the energy going or coming from. So as we go through this, heat flow and heating curve, of water. Very classic terminology there. So we want to start with a diagram like this. Temperature in Celsius on the vertical axis and heat on the horizontal axis. And this can, depending on which way you're going on this, adding heat to whatever you're talking about or taking it out. And so taking it out would start at the high point and go back down the steps, or heat in would go from left to right. And that's the way we're going to do it. So while you draw that, I'm going to lay out the problem. Okay, so here's your problem that we're going to work step by step through. Calculate the total heat energy needed to convert 10 grams of ice at a minus 10 degrees C to steam at 110 degrees C. Now, what you'll need in addition to this are some transition constants and some specific heats, as they're called. And so the specific heats needed is given by a lowercase c. And we have ice will be a 0.50 calories. We're going to work in calories per gram degrees Celsius. Water is 1.00 calorie per gram degree C, and steam is 0.48 calorie per gram degree C. Now you also need in this what we call transition constants. Delta H of transitions, and these are called heat of fusion, that is the amount of heat needed to melt something, and the heat of vaporization, or the amount of heat to evaporate a substance. And those are given by the following. So delta H of F is called the heat of fusion. And for ice, delta H F for ice is equal to 80 calories per gram. And the delta H of V, called heat of vaporization, is given by the expression delta H V to equal 540 calories per gram. So we'll need these at selected times through the calculations. Almost got it all on there. Anybody get this? Okay. I don't need this one. Okay, what we're looking at is 5 heat transition regions. Here is the ice at a minus 25 degrees to 0 degrees, and that's ice only. It's not melted yet. Here in this next slope line is liquid. This is water being heated, and here is your steam up here, solid, liquid, and gas form. Now the horizontal lines, note how they are at the boiling point and the freezing point of water, but there's no temperature change, but there's a heat going in each case. So this is 2 phases in contact, solid liquid in contact, and this is a liquid gas phase in contact. One of the rules that you will need to remember is when 2 phases are in contact, we have no temperature change. When a what's called single condensed phase, like solid, liquid, or gas, the slope lines indicate temperature changes. Now, this gives rise to only 2 equations you need to solve this problem. One for the temperature change regions and one for the phase change regions. And so the Q is what I'm going to use for heat flow, is equal to MC delta T is your first equation. Notice it has a delta T in it. So this equation is used for those 3 regions right there. Of course, the data will be given to you that will fit into that equation, and you calculate an energy number. The second equation is no temperature change region, or a phase change equation. Q equals the mass that's undergoing the change times your transition constant. Now that T can be either vaporization or fusion. And so those deal with these two regions right here. So we'll have a Q1, a Q2, a Q3, a Q4, and a Q5, depending on whether you're phase transitioning or warming or the substance. You select the formula that goes with it. So we'll start with going from left to right. First thing is we're starting at a minus 25 degrees Celsius, right? And to melt this, you first have to get to the melting point. It won't melt until you get it up to the melting point. So in this region, you are warming, and it involves a temperature change. So Q1 is an MC delta T calculation. You have 10 grams of ice. The specific heat for the ice, you can go back and look it up, but it's 0.50 calorie per gram degree Celsius. And then the transition is 10 degrees. It's not plus or minus, it's just 10 degrees. You went up 10 degrees, that's it. You see. And if you look, grams drop out, Celsius drops out, and you're only left in calories. And so that's, I'm going to move it over here, 50 calories. That's what it takes to warm the 10 grams from minus 25 to 0. Now the next region you have to, Q2 region, is a flat horizontal slope. So Q2 uses the M delta H transition, and since it's melting, it will use the constant heat of fusion, the 80 calories per gram times the 10 grams, and we can get the heat needed to melt the 10 grams of ice. So that's M delta H fusion. And so that's 10 grams times 80 calories per gram. Grams drop out, and we have 800 calories. And you keep a running total on this until you get to the end, and you add up the individual values as you go along. So we go now. We've melted everything, and we've gotten it now into all liquid phase. In other words, we're back to, there's no solid liquid interface here in region 3. Q3 is now a slope line, so that's a temperature change region, MC delta T again. And so there's 10 grams of water now, and it's 1 calorie per gram degree C. You can look it up if you want to. And this one is going to have to go to 100 degrees Celsius to get to the boiling point. And so Celsius drops out, grams drop out, and this will give us 1,000 calories. So you continue, region 4 is the liquid gas interface. Notice this is a horizontal line, that means no temperature change. So I would have to use the M delta HT equation here. And so that's 10 grams of water, and that would be a delta H vaporization number. And that's 540 calories per gram. So we have 10 grams, 540 calories per gram. Grams drop. And so that's 5,400 calories in that transition. And then finally, once all of the liquid has been converted into gas phase, now we can heat it from 100 degrees up to 110, which is another 10 degree change in temperature. I'll try to get it down here. Q5 is a temperature change, so that's another MC delta T. So now we have 10 grams of steam, and it's 0.48 calories per gram degrees C, and we're going up 10 degrees C, and that's going to be 48 calories. Y'all back me up on this. I got 6398. When you add those energy numbers, somebody back me up on that. Minus 25. Did I do that? Oh, that should be minus 10. Sorry. Okay, that should be minus 10. So we're starting with a minus 10 going up to 110. I did work it at a minus 10, yeah.
Awesome.
Yeah, I went up through the minus 10, sorry.
I didn't know if you just.
No, I was just
Negative 25 or.
another brain cramp.
Okay.
Okay.
It's Wednesday.
So,
It's close to the weekend.
too much whoopee weed. Anyway, the idea is that to accomplish the total energy, Q total is equal to Q1 plus Q2 and so forth. And as we see, we take 50 plus 800 plus 1,000 plus 5,400 for that region. Each region is separately calculated. And I got 6398. Is that what y'all got, or get something else?
72.98.
What did you get?
72.98.
I think that's right. 7298 calories. Okay, so that's the total energy transferred as you take it from a minus 10 to 110. If you needed that in joules, the conversion factor is 4.184 joules per calorie. And so you can multiply that. 7298 times 4.184, and that's 30534. 30,535 joules, or 30.5 kilojoules. Just divide by 1,000. It depends on what the problem's asking you to convert to. So now, you won't have a problem that'll take you through all of this. The reason I do this is because the problems we're about to start working are fragments of this. And it's called the method of mixtures, in other words, solution phase reactions. The process that's going on uses these equations, but what your problem now is, when you read a problem, you need to determine whether it's a temperature change or not temperature change going on in the process of the working out the problem. So that's where we are now. Oops. Okay, so how many joules will be needed to heat water from 0 degrees to 100 degrees given this? So since that's a temperature change problem, Q equals MC delta T. Did they give us a mass?
It's 250.
250 grams, right. Okay. So we got 250 grams, so that's an MC delta T, and just substitute and solve. So we got 250 grams times 1 cal. I like to work it in calories because it's simpler. And then multiply. 100 degrees C is a temperature change, grams, Celsius, Celsius. And so that's a couple, 25000, 29,000 calories, times 4.184 joules per calorie, whatever that comes out to be. $104,600 joules, and of course that's 105 kilojoules. And so that's first identifying what's going on heat-wise and what are you doing. You're heating or cooling or whatever. That's an endothermic process, as a matter of fact. Because you have to put energy into the water to push it to the higher temperature. So we'll melt 150 grams of ice, I guess is what it was. Now, since we're in a phase change, two phases are in contact, there's no temperature change. All the energy goes into kinetic energy, but you don't see that transferred into temperature. So we use the Q for the melting, mass times the heat of fusion, and that's 150 grams of ice times 80 calories per gram. $12,000 calories. And then if we go to joules, 4.184 joules per calorie. And that's 5208 joules, or 50 kilojoules. And round it off. So it's just a matter of identifying the process, what's changing, and which equation to use. Okay, we're given 174 joules, heated the sample from 25 to 50, and we have a mass of 50 grams. There we go. Okay, so it's temperature change, so Q is equal to MC delta T, but what they're asking for is this specific heat, so you solve for specific heat and substitute and solve. So this is the idea. The heat is 174 joules, the mass is 50 grams, and we went 50 minus 25, or 25 degree change in temperature. 50 minus the 25. And so 174 divided by 50 divided by 25, and specific heat is 0.1392 joules per gram degree Celsius. Those are the units for specific heat. Specific heat is the amount of energy needed to raise 1 gram of substance by 1 degree Celsius. That's what it ultimately refers to. So we're given a mass 150 grams of copper at 100 degrees Celsius, and here's the specific heat of copper. Mass of water is given in the same context. Calculate the thermal equilibrium temperature. So what are we looking at? We're looking at dropping a block of copper into water. So this is at 100 degrees C, and this one's at 35 degrees C. Well, after they mix, you're going to have a temperature final between them, between these two temperatures. Be in the middle here somewhere. Now, this one, the copper is losing energy, and this one's gaining. But the sum of all the energy changes will be zero. Energy lost equals energy gained. You didn't go anywhere like that. So this equation right here, as simple as it looks, when you have mixing of items like this, you can use the sum of all heat changes. Well, what's happening? Well, sum of all the energy changes is Q for the copper, isn't it? Isn't that what's happening? Plus energy change of the water, solvent water that you dropped it into. Now, is the Q for the copper a temperature change problem or not? We're going from 100 degrees Celsius to somewhere in the middle. So that's an MC delta T for your copper. Then we want to add that. Now look at water. Water's at 35, and we drop the hot object in there. That's going to go up to the final temperature. So yeah, that one is. And so MC delta T for the H2O. And all that equals 0. So now, look at the data and substitute it in here and solve for T final. So I'll expand this right now. Let me show you. Take this MC delta T of your copper. Well, what's your copper weight? Also, drop the units out of this. If you're careful with it, they will get in your way. Now, what are we looking for? We're looking for a final temperature. So when at the end of the problem, when we solve the algebra, then put your temperature, your degree C back in, because everything else will fall out anyway. So I'm going to start with the copper, and it's 50 grams. The specific heat is given to be, let me make it bigger for you. Now, everybody can read it? Okay. 0.39 joules per gram degree C. So, okay, that is going to be the, let me put this last one in here. So, how do you get the change in temperature? You're going from 100 to the final. So, the change in temperature is T final minus T initial. So, that's T final minus 100 degrees C. And I'm going to bracket that off and put copper. Now, yeah, right here. Okay, the second energy change in here is this MC delta T, and that's exclusively for what the water is doing. So the water's going from 35 to whatever that final temperature is, and so we'll enter that in. How much water do we have? It says 125. That's 4.184 joules per gram degree C, and it also listed as a T final minus initial. Bracket that, and all that equals 0. Everybody still with me? That's a 0, believe it or not. Now, it's an algebra problem from here to the greatest extent. All right, so it's 150 times 39 and distribute, and then 125 times 4.184 and distribute. And solve for the TF. That's all what you're doing. So 150 times 0.39 equals 58.5 times TF minus 100, and that's still your copper, plus 125 times 4.184, 5523, times TF minus 35, bracket that, that's your water, and all that's still equal to 0. And so we distribute, so that's 58.5 TF minus 58,500 plus 523 TF. That's 18,305, and that's equal to 0. So transpose your values that are negative to the right side, and then add these two. That's let me add that one, plus 58500, 76,805, and then we have 58.5 and 523. and that is 581.5 TF. And so now your T final is equal to 76,805, and 581.5 is going to come out in degrees C. That's what I'm talking about. Wait till the end of it to get the degrees C in there. Okay, adding those two, is that what you got? 24,150, okay. Divided by 581.5. And I got 41.5 degrees C. So that is between 100 degrees C and 35 degrees C. That's where you started with the metal, and it came out in the middle somewhere. Okay, now these were objects that didn't undergo phase change. What if you had one like you're dropping 10 grams of ice and 100 grams of water, or 20 grams of ice into 100 grams of water at those two different temperatures? Okay? Okay, how about this? Let's say we're given 20 grams of ice. That is the word I-C-E. Ice added into 100 grams of water at 25 degrees. Calculate the equilibrium temperature, or thermal equilibrium temperature. So in these, it's always helpful to draw a picture. And so ice has to go through two heat changes. One on melting, and then you're warming ice water. So you have a Q for the solid plus Q for the H2O warming. And down here you have water, the solvent water, and that's strictly one phase, warming to whatever cooling to wherever the ice takes it. So that's a Q cooling. And so you have the ice, I'm going to change that S from ice, solid, ice, that's the melting, and this is warming water, warming the ice water. So you got three things going on, the sum of which equals 0. That is, the sum of all your energy changes equals 0. And that equals the Q of the ice melting plus the Q of the ice water warming plus the Q of the solvent water cooling. Okay, this one has no temperature change with it, so then you have an M delta H of fusion for the melting. Plus now you're warming the ice water, so that is an MC delta T for the warming ice water, plus MC delta T for cooling solvent water. So from the problem data, we want to melt the ice. We got 20 grams of ice, and that's 80 calories per gram. Of course, that would be published under the problem. All these phase change and constants. Now you have 20 grams of ice water. At ice water is 1 calorie per gram degree C, and you're going to warm that to T final. What's the change in temperature? Well, you started at 25 25 degrees C. So there is your warming of your ice water right here. And then, I know it kind of gets crowded. And then we want to cool the solvent water. Well, you set that up. Solvent water, we had 100 grams of solvent water, and that's 1 calorie per gram degree C. Now you're not warming solid, so that's still water that you're warming or cooling, ice water. And so that goes T final and 0 degrees C, that's right. You start at 0 degrees and you go wherever the ice water starts at 0 degrees Celsius. And all that equals 0. So drop out all the units now. And so you have 20 times 80 plus 20 times 1 times TF minus 25, bracket that one, plus 100 times 1 times TF minus 0. I'll just drop that one out. Drop out the 0 and set everything equal to 0. Now it's an algebra problem and one unknown. Solve for TF. Not a problem. 1600 plus 20 onto TF minus 25 plus 100 TF equals 0. So that's 1600 plus 20 TF. 20 times, that's, what's that, 500? I better do it. Dropping zeros. Yeah, just being sure. Plus 100 TF equals 0. And so you want to transfer, unless I misfired, is that just 800? Wait a minute, I'm getting over in zoo. No, it's 1600. TF, that's right. 500 TF. Oh, that should not have a negative going over. I misfired somewhere. There. I just had the temperatures in the wrong place. See, this is the cooling of the solvent water, and it should have the T final 25. This one should have the 0. So correcting that, this should have the 0, and this should be TF minus 25 right there. And so that's minus 0, and correct that, plus 100 TF minus 25. Now it'll smell better after this. And so, let me get rid of that and redo that. 16 plus 20 TF plus 100 TF minus 2500 equals 0. Now it smells better. 120 TF equals 2500 minus 1600. And that's 900. 120 TF. And so after mixing your ice water, 900 over 120, 90 over 12. 7.5 degrees, which is between the 25 degrees and 0. So the ice in there would cool the solvent water down to 7.5 degrees Celsius. But the biggest issue in reactions in solution is identifying who's gaining energy and who's losing energy. Now, one more, and this will be part of our lab issue.
Wait, can you go back up?
Yeah. Where are we? Here is a solution phase reaction generating a temperature change when you mix them together. Both of the reagents and solutions before reaction are at the same temperature, say 25 degrees, but when you pour them together, a reaction takes place and the temperature of the mix goes up to 38 degrees Celsius. So what you want to do is calculate the energy change associated with the limiting reagent in this problem. Which one's the limiting reagent? You've got to determine that. And then once you get that temperature change, that's the energy change for the mass of limiting reagent. Then you have to take that number divided by the moles of limiting reagent in the problem. And that gives you your normalization. That is kilojoules per 1 mole. And that's the way data is published. You don't give out data in 0.2 grams. Now, you might run a reaction at 0.2 grams of stuff, but you convert it at the end of your experiments to kilojoules per mole. This is where we'll start tomorrow. So you take a look at it and see if you can whittle through it and come up with an answer. And we will start there tomorrow and migrate into our demos and experimental work.